Okay, today we're going to have a look at a physics required practical of force and extension. And what we're going to be looking at, it specifically with regards to that, is Hooke's law, which talks about the extension on a spring being proportionate to the mass. So it's important we're talking about the extension of the spring and the increase in mass. What we've got to set up, we've obviously got a clamp stand here. I've got here a 2 kilo weight, which is a counterbalance, because as you can see, the more weight we put on this, the thing would topple forward. So it's important that we remember to put a weight there. I've got a meter ruler up here, standing vertically, and we've got a further clamp with our spring, and on the spring we've got a pointer. The pointer, I've put a red line on so it just makes it a little bit easier to see. We've started, if I just hold that black piece of paper up there, if you actually get down and level, that marker should be on approximately 1 centimetre. Approximately 1 centimetre. We're going to be measuring in centimetres as we go down, and literally what we're going to be doing is adding different masses to see the effect that it has. Now the masses are in 100 grams, which is a simple conversion into newtons, because we're going to be measuring in newtons, and 100 grams is equal to 1 newton. So if we look, we can basically see how the experiment works. We hook our mass onto there. We know that our spring was showing 1 centimetre. So we now put that in there. See where that comes to. Can you see that okay, Bob? For me, that now is showing a length of about 5.3 with 5.3 centimetres. And then we can add, and please remember, obviously the weight, the mass on the bottom of the hook means that the whole unit there should weigh 100 grams. So we're going up in 100 gram masses. So we can see the extension of the spring at 2 newtons. I'd say that's about 10.3. If we go to 3. We've got 13.5 as total length. Four newtons. Uh, 17.7, I'll say that is. Newtons. 21.9. Whoa! Watch it, don't drop your masses. Do get a little bit bouncy, so you're better off to be, the spring gets a little bit bouncy. I'll put that as 26.1. More. 29.9. So that's 33.4, I think. And we'll go to 9 newtons and probably leave it at 9 newtons, which gives us 37.7. Now obviously fairly straightforward. We've got the length of the spring, We know it started at 1 centimetre to start with, so we've just got to subtract 1 centimetre from each of these to give us our calculations. There we go. Now then, what they're asking you to do from there is to calculate. These were some figures we did a week ago, and this is just a very rough graph that I've done based on those figures, and you can see very slightly out. Hooke's law is basically saying that there should be directly proportionate. It should be consistent, the extension with the weight, which means we should end up with an exact straight line. We can see it can sometimes be difficult to read, which is why occasionally I'm ever so slightly above the line and occasionally ever so slightly below the line. But the idea of it is it gives you a graph there of the extension of the spring on the vertical axis, and the horizontal axis is the newtons. Now what this gives us is an opportunity. We take this mass back up to the start. Gives us an opportunity to actually effectively create a Newton metre. You can see there's no real difference between what we've got here and this Newton metre, where, sorry, if I put that on, I think that was 9 newtons. So actually all it's doing is stretching the spring, and we can see that reads 9 newtons. And that's because we know the consistent stretch of that spring inside the metre. And all that we're doing effectively is calibrating, the ruler is calibrating our extension, and that's the purpose of the graph. So it does mean that we ought to be able to weigh reasonably accurately the mass of an item such as this stone using our graph. So we know we had 1 centimetre to start with, and that's it's probably about 9 centimetres that it's gone to. I haven't drawn a graph up for this one at the moment, for this particular spring, because there will be differences with each of the springs. But what we would be able to do is look on here with the previous spring. We can go up our distance, that would be 5 centimetres extension, so that would be 9. If we look across on our graph to there, would give us about 2.5, on our rough calculations, it would give us about 2.5 newtons would be the actual weight of the rock. Okay. That's actually shown us it's 219 grams. Again, if 100 grams equals 1 newton, we're actually 2.2. So we can see the graph on this one is perhaps a little inaccurate, bearing in mind these figures are actually different to the figures that I've just created, so it's actually just a difference in the spring. But that's the idea of it, and effectively that Hooke's law of a consistent extension of the spring under increased mass is the purpose of the exercise, and effectively what we've created is another Newton metre. So I hope that's been useful. Please feel free to create that graph, and I'll be hopeful that our extension would give us a closer answer to 2.2 newtons for the mass of that piece of rock. Thank you very much.